and welcome to the 43rd ETP4HPC webinar. Yeah, I'm still counting. So today we are going to talk about harmonizing Europe's HPC and AI data storage landscape. But before we get into today's topic, I'm Pascal. I'm ETP4HPC's communication manager. My colleague Gabriela is also here to help run the webinar. And for those of you who are not familiar with ETP4HPC, we are a non-profit association that promotes European research and innovation in HPC, and we are a private member of the EuroHPCJU. So some practical information for you. This webinar is recorded. You will all receive the link to the recording tomorrow. This webinar is in listen-only mode. However, you can use the GoToWebinar control panel that's illustrated here to ask questions or download handouts. So today we have one handout. You can download the slides of the webinar. You can do it right now, so you'll have them. You can also submit questions at any time during the presentation using the question tool. However, we will tackle your questions at the end of the webinar. And we'll share the questions in the chat so that you can all see them. So yeah, I think that's about it. So the speakers. So I would like to welcome André Brinkman. He's a full professor at the Department of Computer Science at Saarland University. And our second speaker is Jean-Thomas Acquaviva. He leads the research group at DDN's Advanced Technology Center in France. And of course, Sai Narasimhamurthy is with us today too. He will do a very short introduction. Sai is our strategic research agenda expert. He's leading this effort. So, Sai, before we delve into the subject, do you want to
Yes,
introduce this
sure.
upcoming white paper? Because it's an upcoming white
Yeah,
paper.
of course. Yeah, thank you, Pascal. So, so this is the last white paper in our series of agile white papers. So we had 5 agile white papers during the last year, following our SRA 6. Last but not the least, a very important one. So what we are trying to do in this white paper is showcase the importance of storage, especially as things move to AI. I think because we feel that this is an ignored topic in some sense. So storage and IO had been addressed in the past in the calls in the 2010s, but somehow it has dropped off the radar. And the requirements for storage and IO, it's really changing for AI. And it's a high time for us to start looking at what the changes are needed for and what can be done for the new AI workloads from a storage and data perspective, and what kind of storage platforms needs to be built, especially in the context of AI factories and things like that. So it's a very important white paper. So just to give a picture of what Andre and Jean-Thomas intend to do here today. So with that yeah, that's the quick introduction to the context of the white paper. And just a quick note that after this, we are going to start the SRA 7 activity in February. So there's going to be a lot of work on storage and IO in the new SRA 7 as well. So I look forward to the attendees' feedback on, yeah, please keep yourself posted on the new activities here.
Yeah,
Back to you,
actually,
Pascal.
I just wanted to say a word about the upcoming white paper. Once it is available, I will send the link to all webinar attendees. That's what I did in the past when we talked about future white papers. So to all attendees today, don't worry, I will send you the link once the white paper is available. So time for our speakers. André, Jean-Thomas, we're very happy
Okay.
to have you here, and the floor is yours.
Okay, thanks a lot for having us. So this is a two-head presentation. So first myself, I will do the first part, and then André. So I have, of course, to thank a lot André for having worked on most of this slide, actually, even not all, right? This being said, what we are going to present you is not just the work of 2%, but this is the summary of discussions that we have started almost like 1 year ago in order to build this white paper. So there is around 20 researchers that has been involved in the definition of this document, and we try to extract, I would say, some kind of line of thought. It's of course an oversimplification, so you will have to wait for the full document in order to get the details. So the topic today, as introduced, right, is about a European data platform. So in order to get to this point, we have a very simple outline that why a data platform, why storage is important, specifically in this time of AI and for the AI workflows and workload. Then we will discuss the sovereignty gap. So do we depend only on a non-European manufacturer, non-European technology? I don't think this is the case, but we will discuss this a bit. Do we have a window of opportunity in order to push and to crystallize the existing European expertise? You know that it's, I would say, world-class, but maybe there is a way to crystallize it in order to implement something. As an example, we will discuss a possible European KV cache solution. So because KV cache is one of the hottest topics today in storage, specifically in AI inference. And then how to action this, how to implement these ideas. So what is a call for action? That will be our conclusion. Next slide, yes. So why no? So why do we want to reinvent the storage stack at this very peculiar moment? So, of course, if you look at the context and also a bit in the rear mirror, we are ongoing kind of disruption, maybe not a revolution, but that says there is a discontinuity in the evolution trend of technology. Since we have been in this field since quite a years, right? It's not the first time that we see this kind of inflection point. So for those who were around in the late 90s or early 2000, the dot-com bubble or burst, I mean, the dot-com era was really a major inflection point. So suddenly we see a new world of possibilities popping up just right in front of our head. And consequently, many technologies that we are using today, thanks, for example, for this webinar, are coming from this time. More recently, we had, you know, the personal computer in the pocket. So we all know have a smartphone. It's very recent, and it has also led to a huge amount of innovation. And for example, the emergence of ARM as being a ubiquitous platform. And something that has been a bit overlooked in our community, specifically, I would say HPC community, numerical simulation, the cloud computing. So these guys, they have really pushed new technology in a very important way, and also they have defined the industrial landscape. That is maybe somehow one of the bottlenecks that we have to address today. All of this disruption, right, this inflection point were a good opportunity, at least in the past, to revisit the existing legacy. So for instance, when we had this arrival of what we call the killer micro, so basically the shift from specialized processor to standard personal computer microprocessor in the field of numerical simulation, this led to a huge amount of parallelism. And we had to redesign most of our software stack in order to handle this change in the order of magnitude of parallelism. And in the world of storage, for example, we designed parallel file system. So GPFS and Lustre are the two most well-known examples. And there are also two very active on living technology. So Lustre is, I would say, powering most of the AI system today in the world. So it's just a reminder that it was a good investment. 25 layers, we are still, you know, harvesting the fruits of this investment. The cloud people, they implement somehow today what is a de facto standard, S3. So it's coming from the cloud. On S3, I just would like to remind that it means simple storage service. And there is two very important keywords here, is simple and service. So service is kind of a paradigm shift that also may need to be addressed in future storage technology. From a hardware standpoint, we had the emergence of the flash device or SSDs. So these devices are so powerful in terms of bandwidth and low latency that they completely shake the existing architecture. So they have pushed for this notion of hierarchical storage management, where you have different technology, hard drive and flash cohabiting into a single unified namespace. Next slide, please. Yes. Yes, next slide, please. So we are not the only one to say that, this is storage is important. So today, the most important person in our field is clearly Jensen Huang, and he just makes some obvious statement, right? A computing platform, a system is basically three pillars: computational engine, so the processing part. So for Huang and NVIDIA, this is obviously GPU, right? The networking technology, and here, interestingly enough, we all know that NVIDIA bought Mellanox, another HPC technology that seems to have been extremely successful in the field of AI. And for the storage, the end of the quotation is that, it needs to be completely reinvented. So I suppose this is also highlighting the need for disruption in the world of storage. Next slide, please. So why there is a need to reinvent the storage stack? So today, the disruption is coming from this AI workflow. So AI workflow, usually you can, make a clear distinction between the training part and the inference. So training is the most well understood part, probably because it has been around since a bit more time. And for people coming from HPC, this is a very similar workload than a traditional HPC system. So lots of IOP, and it's very write bandwidth intensive due to the checkpointing. So we know this well, and the HPC technologies has been very efficient about helping the training to deliver good performance and being efficient. Now, the new technology, the one who is really attracting all the market, is inference. And inference, it's a bit more complicated, notably because originally we thought it was a no-brainer. Oh, it's easy, it's mostly a memory bandwidth problem. But the inference, there is so much economical importance to it that it has been notably more, how to say, specialized. Sorry for my English. And as a result, instead of just tracing the memory bandwidth, the researcher and innovators, they are now putting pressure on much more component of the system, notably the storage. Why? Because the evolution of inference starts from very small context. So everything could be stored in the memory, and now the contexts are much larger, so in the range of millions of tokens, that it's not fitting anymore in the very precious and scarce resource that are the HBM. It has to spill over the storage, so we have to cope with this workload, and it's actually a very powerful enabler for the GPU efficiency. We are somehow not critical in terms of importance in the architecture, but we are on the critical path. It means that a slow storage will basically slow down the full system. So if we are smart enough and we can hide the data movement, then the GPU will be able to run full speed. Otherwise, they will be basically limited. The bottleneck will be storage, and the very important investment on the GPU part will be inefficient and with a weak return of investment. Next slide, please. So a bit of discussion on, we have two slides here on the checkpointing, right? So checkpointing, originally, it's coming from this attack of the killer micro. So we have a lot of parallelism in our system. We have many, many discrete components. So there is a non-negligible probability that during a computation, one of these components will fail. So how do you cope with error? So the most obvious thing is that, I will restart my computation. Okay, fair enough. But now that we have thousands of clients in the system, it's not really optimal. Furthermore, for the numerical simulation, we used to have my code is going to run for 24 hours. It's considered a very long running simulation, even if, of course, we had something more aggressive, for example, in the climate simulation. But for AI, training can take days, weeks, or even months. So the risk to take by just not doing checkpoint is extremely high. Furthermore, there is some inherent condition of the training, is that by design, you need to keep a journal of the various version of your model in order to be able to backtrack, because the training is a non-linear phenomena. So you may need to backtrack a bit in order to find the latest, most performing version of your model. So there is a strong need checkpoint, not only for to protect from the mean time between failure of the individual component, but also just to help the data scientists to get the best model. So it's not just an efficiency question. So if we can go to the next slide where we have a zoom on this plot. So here you have three things. So they are, I would say, kind of simple. So the blue one is that, okay, I don't care about the mean time between failure of my individual component. I will run without checkpoint. So of course, as the system is getting larger, you get some caught back by the failure rate. So you see that somehow, if the size of the system is reaching a very high number of GPU, the probability to have to restart your computation is somehow increasing. So you are decreasing the efficiency of the system. So to protect from the failure, we will use checkpointing. So this is the red plot, and this is, I would say, a straightforward checkpointing strategy. I compute a version of my model, I dump it to the storage, and then I compute the next version. While I'm performing the data movement, I will wait for the storage to ingest all the data, and then I will resume my computation. While the system is growing, the volume of data to save is increasing as well, so you have to wait longer and longer in order to do this data movement operation. As a result, of course, the trend, I mean, the efficiency is going down. So one obvious thing would be to increase the storage performance, but there is some physical limitation to this. So you can go from smarter checkpoint strategy, one of them being the asynchronous checkpoint. So here the idea is very simple, that I compute a version of my model and I start right away to compute the next version. And while I'm computing, I will do asynchronously, I will save the previous version on storage. So it means that somehow I'm overlapping memory data movement with computation. This is thing that we have been doing in HPC for years on years, is extremely effective. And you see the red plot is clearly outperforming the synchronized checkpoint strategy. Next slide. So in both cases, thanks, André. In both cases, these are kind of straightforward checkpoint. In HPC and today in AI, there is many optimizations that can be injected. If you talk to people from SCR or multi-level checkpointing, they know how to leverage the existence of some additional layer in the storage stack. For instance, if I have a local drive close to my node, I will first write to the drive, let's say 10 checkpoints to the drive, and one checkpoint out of 10 will be written to the centralized storage. So I can decrease by a factor of 10 somehow the data movement to the centralized storage. So it's working very well. I could do also smarter things, a bit more like, MPI IO aggregator, where you trade somehow GPU to GPU bandwidth for storage bandwidth. So one node is elected as a storage leader. It will aggregate the local data from neighboring GPU and then do the data movement itself. So this strategy, they have been tested and validated in HPC, very efficient, and we expect that they will end up in the storage, in the AI stack in the nearby future. And okay, so this plot is just to remind what you can get out of this smarter way to do data movement. So there is a 40% improvement. So it's basically cutting by half the need to have faster storage. So it's important. There's a lot of things to gain here in terms of efficiency. Next slide, please. So now let's talk a bit about the inference. So inference is the hottest topic today. So in order to infer, we have a probe coming to the system. So the probe is just like a simple sentence. What is a future of a storage stack? And the system will decompose this probe into token, and then the model will apply to the token, and that's marvelous. That was the initial way to do inference. Now there is this notion of additional context window, where basically the system is able to generate additional question, or also to keep track of the previous question from the same user. Because the system is generating itself additional questions, so derivative question, what is the future trend of storage? It will ask future trend from a scientific standpoint, economical standpoint, sovereignty standpoint. So the system will generate additional question. All these questions will generate additional token. All this token will be processed in parallel, and then at the end you have kind of a reconvene point where we aggregate the result and we deliver the most accurate answer to the end user. So the context window is moving from few tokens to up to 1 million in modern system. So 1 million token it's putting a lot of pressure on the memory. If we look at not even the largest model, but the Llama 3, 70 billion parameters, a 1 million token window, which is basically what you can get on Gemini today, it's about 300 gigabytes of memory. You cannot afford to have 300 megabytes of memory. You need to move this to a storage part. So initially we saw that, okay, it's going to be about inference, is about loading a model. So I have to load few megabytes of data, but no, actually there is a lot of write. These write are non-regular in the sense it's more like a small write all over the place. So the average inference write is about 120K in a random order. The model are keeping bigger. So we said, oh, okay, with the DeepSeek, you know, the small model are going to take over. It's not the reality. Models are still getting bigger, so they are generating more tokens. There is more complexity attached to this. So the KV cache, so the volume of data you need to store in order to save memory is going to get higher and higher. So more pressure on the system. Next slide, please. So this one is really interesting because it's bringing something that is also a bit overlooked. So let's go just for the plot on the left part of the slide. You see there is some vertical bar, threshold 1, 2, 3. The fact is that in inference, at the opposite of training, there is a human in the loop. There is an end user waiting behind the screen, and people, they don't like to wait, right? So it means that there is a notion of time to result. Threshold 1 means basically the perfect quality of service. I'm able to answer to my user in less than 100 milliseconds, which for human beings, this is basically the speed of reading data. And then after you can degrade some of the quality of service by allowing to build more batch. So you trade bandwidth for latency, but you degrade the quality of service in the sense that the user is going to wait more. So basically you are stealing a bit of the time of your user, but you can deliver a more accurate answer. If the KV cache, so threshold 1 here, we see that when the KV cache is enabled, Mooncake, so it's basically a Kimi system. It's a very large system in China, 24,000 GPU. This Mooncake system is implementing KV cache and it's accelerating, it's improving some more the high accuracy, low latency answered by a factor of 7. So 500%, it's a factor of 6, pardon me. So KV cache is not only a way to save memory, it's also a way to improve the quality of service. So, yeah, okay, next slide, perfect, no. I just wanted to mention also on this plot, this notion of efficiency. So if you look at this machine, the Kimi machine, they claim in a recent paper that they're processing 100 billion tokens per day. So it's about 4 million tokens per GPU. The individual peak performance of each of these GPU in the order of 200 million tokens per day. So there is a factor of 50 between what they observe in production and the peak performance that the system is able to deliver. So there is a lot of room for improvement. There are various factors to explain why the production performance is not matching the peak performance. One of them being actually the size of the context window. Next slide, please. So as we are heading toward larger context window to improve the accuracy of the answer, what do we have here in our nearby future? So if you look at what's going on in AI, so it's a bit like the Bob Dylan song, you know, the time are changing. It's always changing, but it's changing in a single direction, more and more. A better accuracy, and we want to have very good response time. Next slide, please. So the problem is not going to disappear. We have to address it. There is one thing also still in this discussion about data on storage is that today most of the data management is done by the CPU. This AI node, you know, there is the GPU. They are still branded as accelerator, and they are hosted by a single GPU. So one of the questions that you could ask is that why do we need to talk to the CPU in order to talk to the storage? Is there a way to talk directly to the storage so to reduce some of the data paths? This has been done by NVIDIA. So they are promoting this GPU direct storage solution. It's not the only one on the market. And the idea is to basically to reduce the data path. And the improvement is not only in bandwidth, it's in latency. And again, we know that for inference, latency is one of the key economical parameters. Okay, so here we see the results that have been obtained by the research community by trying to not offload, but at the opposite, inload part of the storage management within the GPU. So GDS, so this is the NVIDIA technology, is just part of the answer. Actually, you can do more things. It has been addressed by the research community quite early. So GPUFS, I think it has been proposed 10 years ago at ASPLOS. So people already start, okay, let's try to modify the kernel, the firmware running on the GPU in order to support a POSIX interface. Actually, it's stumbling on some limitations. So GPUs are magnificent parallel machines, but they are not very good about dealing with the complexity of storage. So there's a lot of branch on indirection when you manipulate data on file system. So it's not a task that GPU are well organized in order to address. CPU is much more versatile. So more recent research like Gemini FS, coming from China again, what they try to do is to offload the data path on the GPU and to keep just a part of the file system management on the CPU, all this metadata management. And you can see there are the orange part that actually they can decrease the latency by 1 order of magnitude, even in respect of GDS, which is already an optimization. To my knowledge, AMD does not have at the moment GPU direct storage. So by being clever, you can get 1 order of magnitude better latency. And again, latency is a critical part in inference. Okay, so you can address a bit more of the complexity of, what does it mean to do file system in GPU, but maybe we can jump to the next slide for the sake of time. And here I will hand over to André, but first I just would like to underscore one point. So I'm coming from the industry. André is coming from the academia. And I think this is one of the strengths of ETP4HPC is that you have people from the whole community looking at the same problem.
Exactly. First of all,
Thank you.
Thank you very much,
Thank you.
Jean-Thomas, for doing the academic part of our presentation. And we decided that Jean-Thomas will more or less present the first part, which is more in-depth technologically. And I will talk a little bit about the storage sovereignty gap, which we both see here in Europe. Okay, so I think it's obvious that Europe's AI and HPC infrastructure is heavily relying on non-European storage. It's not only storage, it's also GPUs, it's CPUs. There are endeavors being undertaken at the moment by the European Commission to change this. And what we want to show here is that it makes sense to also undertake such endeavors on storage, and that it's also the right time to do this. So also, if you take a look on who's dominating AI at the moment, it's clearly NVIDIA. They do not only dominate in GPUs. Jean-Thomas already mentioned it. They bought Mellanox and are therefore a heavy lifter in networking. And they are more and more also pushing into the software domain. And especially the software makes a difference for them at the moment. Also, if you take a look on what they are doing in storage, they have invented GPU Direct. This is one technology, but also they have invested in so-called DPUs. And DPUs are data processing units. And these data processing units are more or less smart NIC cards. And what they want to do is that they clearly adapt existing storage infrastructures and even more tightly couple them to their NVIDIA GPUs. And what you also see is that a lot of these software OEMs and the software developed by storage OEMs like VAST, DDN, Waker is more and more tightly attached to the NVIDIA infrastructure. And so far, the dependency even increases on NVIDIA. And of course, this is a risk of vendor lock-in. And we have to think about whether we want to have such vendor lock-ins, especially if you take a look on the global political situation at the moment. Therefore, we think that it would really help if we have some kind of European-owned storage technology, which would enable us to, on the one hand, of course, have a stronghold here on this technology itself, but also to be more able to choose between NVIDIA, AMD, perhaps emerging European chip makers. And therefore, we think that investing in storage really keeps the value creation, jobs and innovation here in Europe. Of course, if you want to go in such direction, there also has to be some kind of opportunity. And we think there are lots of opportunity. The first one is that we really have changing requirements. If you take a look on how complex it is to develop software for HPC, storage HPC, then you see that in AI frameworks, you really can benefit from a more relaxed storage semantics, and that many of the tasks are read-only caching, which makes it simpler. And a second point is that already the infrastructure is more or less provided by the AI nodes themselves. They include a lot of NVMe storage, which could become the foundation for some kind of distributed storage infrastructure, which still has to work together with backends like Lustre or Weka or whoever, but where you can have a wonderful caching infrastructure. Then, of course, you have the GPU Direct, which is not that well used so far by current providers, and where you can also offer something like distinction from what's available at the moment. And the same is valid for the DPUs, these data processing units I described on the previous slides, which are becoming more widespread and which are definitely offering new opportunities to offload part of the storage management from the GPUs and from the CPU to these DPU cards. And therefore, we think that there is some kind of strategic opportunity so that we really can leverage these changes in hardware and software and to provide something which is new, which is different from what is existing on the market. A second point is that there is a lot of knowledge on storage in Europe. So in the last funding period, there have been two big projects funded by Euro HPC, which completely focused on reinventing more or less the storage infrastructure for HPC. And we will show that these inventions, which have been more or less being built and prototyped in these two European projects, also can be easily is always a nice word, but it can be transformed into an AI software environment. And these projects have been Admire and IOC. And many of the people who have been helping us to write the white paper have been also partaking in these two initiatives. So therefore, the second strategic opportunity is that we really have the knowledge here in Europe, which is necessary to build up such a large-scale AI storage systems. Jean-Thomas and I decided that we will provide one example on how you can more or less leverage this knowledge. And we're now talking about the so-called European KV caching solution. And of course, if you want to build a solution, you have to build it on top of some existing hardware. And as an example, we've taken an NVIDIA DGX B200 node. And if you take a look, it already includes 8 3.8 terabyte NVMe SSDs, which is more than 30 terabyte per node, and with a performance of up to 80 gigabytes per second, which you can get out of them if you want to read or write to them. In addition, you have more than 4 terabyte, of course. It's much more than I wrote here of DRAM in the system, which is more or less can be combined with the underlying storage system. A second point, which is a little bit different from what we know from HPC, is that the network interface of these AI nodes is much more powerful than what we've seen before. A typical DGX B200 node includes more than 8 times 800 gigabit of performance, of networking performance, and additionally has these two Bluefield 3 cards, which are these data processing units, which can nicely be connected to backend storage systems. And the question we ask ourselves is it possible to move the KV caching to this node local storage? And fortunately and unfortunately, it's not that easy, because Jean-Thomas has already shown if you have hundreds of billions of tokens which you handle each day, then you have hundreds of petabytes of storage which you need to really store all of these context windows within your system. And this cannot be done on node local storage or on one node local storage. So you have to build out of this some kind of distributed system so that you combine and aggregate the storage which is inside of these individual nodes. And now I'm going back a little bit to HPC. What Admire and IOC have been working on is on so-called ad hoc file systems for HPC. And they originate in supercomputing, and what they do is they combine the storage capacities within the compute nodes of an HPC system, and they provide it as some kind of uniform namespace, single namespace to applications running on these systems. And normally these ad hoc file systems are running in the context of a single application, but you of course can also run them within the context of workflows or bigger systems and longer term systems. They work closely together with backend infrastructures like Lustre or GPFS, and they have been deployed already on a number of supercomputers like Frontier, Summit, Fugaku, also in China, of course, on the Sunway new generation supercomputer. Here in Europe, the most active players, and I hope I don't forget too many of them, are BSC, Barcelona Supercomputing Center, also Madrid, UC3M, has been heavily involved. In my former position in Mainz, I've been taking part, now moving, of course, this knowledge to Saarbrücken, and we've been closely working together with a technical university in Darmstadt. And within this project, I think we built up a lot of knowledge on how to handle such systems. Here are some numbers on how they already help in HPC. And here we took the results of running HADA-FS on the Sunway new generation supercomputer. This has been work from Tsinghua University. And it's interesting to see it because Sunway new generation supercomputer is just a scale out, one of the large systems in China. And they have scaled up running ad hoc file systems up to 480,000 processes. And what they have been able to show is, and you see this throughout the table here, is to more or less remove completely the IO from the critical path, which means that in the beginning, for many of these applications, the impact of IO on the overall runtime was in the order of up to 15%. And they were able to decrease this impact down to 2.6% for lattice Boltzmann, or even down to 1.5% for plasma simulations, and even to negligible numbers like 0.1% for other applications. So in principle, they have shown that they really can help to overcome IO bottlenecks, and we now want to move this to AI. If you take a look on how they are designed, they are software only. So here's an example of our own ad hoc file system, which is called GeckoFS. And within GeckoFS, we have taken the standard infrastructure of HPC nodes, or you can also say the standard infrastructure of AI nodes, and have added some additional software functionalities, running a server on each of these nodes and running a client on each of these nodes. And the servers, the clients are more or less intercepting all requests to the underlying storage systems, to the underlying file systems, and they're deciding whether they can serve it locally, whether they have to forward this information and this request to another node, or whether they even have to forward it to the backend Lustre file system. And nearly all of the ad hoc file system available on the market today have a very similar architecture. They are built in a modular fashion. They are taking libraries like the Mercury IPC library for networking or Argo bots, which both have been developed at the Argo National Institute laboratory. They are taking things like RocksDB for metadata, and therefore they already combine a lot of tools on metadata and communication to be able to really build something which is production ready, even if it is coming from an academic institution. And also things we work together with other partners, for example, here with Tuda, it is closely coupled now to the backend file systems. For example, with the GLASS system we developed for GeckoFS, you can more or less use Lustre and the underlying ad hoc file system as a single unified namespace. And therefore we rely on previous work from the Lustre community, who has developed this Lustre persistent client-side caching, where it is possible to use the HSM, the hierarchical storage system within Lustre, to move data not to a slow backend tape-oriented storage, but to move it to this faster node local storage. And GLASS builds on this experience of using HSM and combines then more or less the HSM interface of Lustre with the Gecko file system. And within an additional layer, we can then always decide, can we send it to the ad hoc file system? Do we have to send it to Lustre? Or do we even have to move back data to Lustre because there are conflicting requests from other applications coming to the file system? Current work which is going on is that all of this is integrated with Kubernetes and the standard AI frameworks, so that you can more or less provide it out of the box, and it then can serve as a complete training and caching solution based on technology which has been developed in Admire and IOC. So, and if you then take a look again on this hardware which it can provide, and that you need between 1 and 100 gigabytes per second per GPU to avoid stalling of GPUs, then you can see that NVIDIA has nicely more or less outlined their node infrastructure in a way that it fits with the storage requirements coming out of it. I already mentioned it, the NVMe SSDs can provide up to 80 gigabytes of storage bandwidth. We have this 4 terabyte of DRAM per node, which can then serve very hot data. And we have 800 gigabyte Ethernet connection to distribute more or less the storage and the KV cache over the system. And when you then build such a KV caching solution using this existing ad hoc file system and combine it with host DRAM, and with an intelligent scheduling in your system, then you can really serve very huge inference settings. And Jean-Thomas already has been talking about a moonshot AI, and more or less the mooncake solution, which was presented last year at Usenix Fast conference, is being built based on the experience which Tsinghua University has made with their ad hoc file systems, which, and this is, we are a little bit proud of this, is based concerning the architecture on the Gecko file system developed in our group. So therefore, there is a strong opportunity to transfer this. The question is, what do we have to do next from a European perspective, and what is the outcome of our discussions we had within writing this white paper? And the first thing is, of course, AI is changing so fast that we have to take care that we really understand upcoming new access pattern, upcoming new applications, so that we really can adapt to new requirements. And only this makes it possible to maximize the GPU's utilization if you feed them with the data you need, and otherwise you have some kind of wasted capital. And what we already started also in Europe here is to start tracing initiatives. So that we want to deploy a unified tracing infrastructure and profiling infrastructure for storage on the big AI factories and the big HPC system, so that we can see where bottlenecks come from as soon as possible. And we want to collect this tracing data within archives which we open to European and worldwide researchers, so that based on this tracing and profiling archive, both companies and researchers have the opportunity to really adapt their systems and to enable a higher GPU utilization. The second point is, of course, we need some kind of converged data platform, and we need pilots which we build up here in Europe and which we use here in Europe. And in principle, in line with the program to develop a European processor, we also have to have a program where we build a converged data platform and where we deploy such a platform, perhaps similar to what the Synergies project is currently doing for other technologies which have been developed in Europe. We personally see open source solution as really an attractive and viable strategic path, which can really couple nicely with the experience on Lustre we have here in Europe. This is also where Jean-Thomas comes into play, because the company he works for, DDN, of course, is the strong player in Lustre. And if we combine these technologies, if we combine this experience we got from previous results, then we are able to really build something with a very high TRL level as a storage pilot, and which could be a nice starting point for storage technology coming out of EURES. In parallel, therefore, we also have to see what do we want to do on the hardware level. Do we also need an embedded hardware development program? We think yes, perhaps we are not as far with hardware in Europe as we are at the moment with storage software, but also there it is important to have some seed funding in a sense that we can also become more independent concerning storage hardware. So I already want to come a little bit to the summary and the lessons learned we got from writing this white paper. What we've seen is AI is changing everything. So if you want to be important in academia and in industry, you have to offer solutions, because this is by far most growing market we have today in IT. Currently, we are very dependent on US and China, and we are not allowed to become even more dependent by neglecting storage. And especially storage software is one of the strengths we have here in Europe. And the weakness perhaps is we don't have a $1 trillion company like Microsoft, like Google, like Facebook. So we have to more or less combine the strengths we have, the academic strengths, the medium companies we have, to build a unified open source data platform. And we have to be aware that this is expensive, because funding typically requires a critical mass. And just taking a look on Lustre, behind Lustre, there are more than 120 people contributing to Lustre. This is most probably also the order of manpower we would need here in Europe as a good starting point to build up our own storage industry. And definitely, we shouldn't neglect hardware in the midterm. We should have some seed funding here in interesting projects. And definitely, we have to observe the past to predict the future. We have to learn what is coming up. And we have to find answers here in Europe on how to position ourselves in IT and in industry. Thank you for your attendance. And we are open for questions now.
Thank you, André and Jean-Thomas, for this very interesting presentation. So it's now time for questions. Actually, we already have some questions. So, sorry, I need to share my screen. Yep. Okay. So I encourage you to open the chat so that you can see the questions, and I will take them in order and read them for you. So we had the first question from Lampros Maradzakis. In the CPU-centric diagram, the bottleneck is clearly the CPU memory bandwidth. In the GPU-centric model, the data moves over PCIe. Since PCIe is often slower than local memory bandwidths, does the GPU-centric approach eventually hit a wall limited by the PCIe generation, Gen 5, Gen 6? So who wants to take this one?
I take this one.
Okay.
So that's a very good point, actually. That's a very good point. So I have some element of answer. So if you open one of these DG box and then you go to the storage, you can go to the local storage or you can go to the remote storage. Actually, the performance of the local storage in terms of bandwidth is lower than the performance of the remote storage, still in bandwidth. And it's boiled down to the number of PCI lane. So PCI lane is really the limitation in terms of bandwidth. Of course, if you go to latency, the local storage is just like much faster, much more reactive than going over the network. But still, bandwidth-wise, you take the number of PCI lane on the block diagram, and then you can define somehow the bandwidth of your system. And I would say also that the bandwidth of PCI is still increasing at a very high pace. So, for instance, in modern system, a single PCI Gen 5 SSD device is about 8 to 10 gigabytes, just a single device, and there is no way that we can move data over the network at the same speed.
Perhaps an important aspect here is also that it's not only about the hardware. Of course, Jean-Thomas is completely right. We now already have increasing bandwidth to the network, to the outside world, to distributed storage, also to local storage. But it's also a lot about scheduling, because of course it's always the best thing to use data which is already in your HBM, that you don't have to reload it from somewhere else. And if you take a closer look on these KV caching strategies which are out there, you see that they of course try to move requests from clients and from customers to the nodes where the data is already in the GPU HBM memory. But then in the second stage, of course, you cannot always keep the data or the request exactly there where the data is. And then you have to have something like node local or distributed storage where you get your data from. And I think exactly this interplay can help to improve this GPU utilization as far as possible.
Okay, thank you. So next question is a question from Henry Strauss, and it's for André. Talking about the European KV caching solution, you still are relying on NVIDIA, that is to say US hardware, DGX. Do you see a chance that this will change in the foreseeable future, for example, by using parts from EPI? That's a big question.
Yes and no. So the DGX example, of course, was just because it's so widespread. And I'm currently building up a new center for AI in Saarbrücken, and my current customers typically ask me for NVIDIA hardware. I hope this will changing a little bit. And of course, we should also try to get as much from EPI into the systems as possible. But at the moment, for inference or also for training, there are no real alternatives from my perspective to NVIDIA GPUs or AMD GPUs. And we have to live with these realities. And we have to start to become independent in different directions. On the one hand, on storage. On the second hand, of course, I hope that there will be similar initiatives for training and inference hardware. And then, of course, if we have a European ecosystem based on storage software, based on AI software, scheduling software, it is much easier to integrate this into the overall system than if we don't have it. And in summary, we have to become independent in different directions, not only on a single one.
Okay, so we still have time for, we have one last question, but we still have time for more questions. So please enter your questions in the questions panel. So next question is from Matteo Mascani from HPC. Matteo, we are delighted to have you today with us. So Matteo says, thank you very much indeed for your very interesting contributions, since the HPC data storage is a key element in performance. Question, as a general trend, computing-intensive data crunching moves from CPU to accelerators. Moreover, the general trend in computing-intensive data crunching of highly heterogeneous datasets from large to non-large dataset is the bare metal computing with direct interconnection, no syscall, no involvement of CPU, between accelerators and data storage, for example, as provided by some leading US suppliers. So do we have similar solutions that we can buy and implement in Europe, please? Who takes that one?
I will maybe use this question to do a transition with the previous question. So what we do see on the market, right, is that at the moment we have a single hardware to do inference and training, and it's widely expected that actually it's going to fragment. So we will see chip dedicated to inference, chip dedicated to training. And there is already this for hyperscaler. So AWS, they have their Trainium chip and they have their Inferentia chip. So Inferentia chip is optimized for inference. Interestingly enough, Inferentia is based on ARM core. So we have some European ARM technology. Now to get to this notion of can we use the bare metal only, and do we have a European alternative? So I think it has been addressed by the people from Gemini FS, where basically they keep the CPU, right? But they, by pure software technology, pure software development, they show that they can improve quite dramatically the performance in respect of GDS, which is one instantiation of direct access, right? By being clever on putting the data part on the GPU, on the control part on the CPU. It's a software solution that's been done by a Chinese university. I think we should be able to do something equivalent.
Thank you.
We are definitely working on it in Europe. But the point is we don't have the solution. And this is perhaps also one interesting thing. On our last slide, I mentioned that even Lustro needs 120 full-time equivalents. I was talking to the head of the development at Tsinghua University, and I asked him how many people are working on their storage solutions for AI, even at Tsinghua University. And he just mentioned a number which was significantly bigger than 100. So this is something which is not yet existing in Europe, that we are more or less consolidating so much also development power in single universities or in single projects. But we have to think about whether we should do that so that we can really speed up the development in Europe.
Thank you. Then we have a question from Philippe Segers. Any link with work performed by UDAT on data management or with work on federations such as the one from Phoenix Infrastructure or Simple? How does that cope with heterogeneous systems at European scale? And by the way, Philippe comments, and thanks a lot for the very interesting webinar.
Yeah, what I can say is
so who takes that one? Yeah, you, Andre?
Sorry, perhaps I can start and John Thomas takes over.
Yeah, go ahead.
When designing the white paper, distributed storage played in the beginning an important role, and especially distributed data collections like the one by UDAT. We have slightly removed this from this white paper because it is a little bit an orthogonal topic. We have to have the data in Europe. We have to have the data archives, the data collections, which are the foundations for training and also for including this even in inference in parts. But it's the pressure on the infrastructure comes more from the actual training itself and from the inference itself. And so we haven't included it that prominent in the white paper as we were thinking first in our discussions. Jean Thomas, can you comment on this too?
Yes, so that's a good question actually, and I would like to make a bit of additional comment here. Is that if you look at this Kimi machine, and I think this is something that is very interesting, is that the people putting the system in production are also putting research on the top of it. So it's allows them to have a very tightly coupled virtuous circle from production to development of new solution. And of course, for Phoenix infrastructure, so this notion of interconnected infrastructure, I do see different way of interconnecting this on allowing site to exchange production information. What's going on at CA in terms of data management, like tracing information? What can I capture on the monitoring system of Ulich? Then if you can already exchange this information, Why today production system and research are completely segregated, right? It's very difficult to get information. I think it will accelerate notably our capacity to develop new solutions. And of course, ideally, this notion of having instrumented system, production system being able to talk to each other, I think would be highly beneficial. But for the moment, there is no formal link. There is a conceptual link.
Thank you. So, well, it's time to close, but I would like to go quickly go through the last questions. So we have a question, another question from Henry Strauss. André mentioned the importance of scheduling in the context of I/O. How do you see the recent acquisition of Slurm by NVIDIA? Won't this mean further dependency on US technology?
In principle, shocking. Slurm has been US technology all the time. It is open source, and I hope it will stay open source. But I mean shocking because NVIDIA is even acquiring more technology and making it a more monolithic system than it has been before. And of course, this makes it even more difficult to break out of this NVIDIA dominance. And from that perspective, I think it's pretty hard.
Yes, I think it's a rhetorical question, right? So working for a US company, I'm not that concerned that we are, dependent on the Slurm being a US technology. What I'm a bit more concerned is that it's consolidated with a single actor.
Yeah, exactly.
But it's also an acknowledgement of the importance of the topic, definitively, yes.
Okay, then I think we're done with the question. We have a nice comment from Sergio Rivas Gomez. Not really a question, but thank you for your time and for putting this talk together. Though I think it's a fitting conclusion for this webinar. Thank you very much, André and Jean-Thomas. Sorry, Gabriela, you confirm there are no more questions?
Sorry, there is just a request for the link to the white papers. I'm very sorry for my voice today.
Yeah, okay. I will. Yeah, concerning the white paper, I will say the white paper is not published yet, so I will make sure that I send the link to all attendees, all of today's attendees, once the white paper is ready. I've done it for previous webinars. I won't forget, so I will do it, but it will be a few weeks until the white paper is ready. So yeah, so thank you, André. Thank you, Jean-Thomas. This was a very interesting webinar. We had a lot of attendees, so well done. The topic is obviously interesting to many people. And thank you to our attendees. And I don't have a date for the next webinar, but you'll receive information about upcoming webinars. So hope to talk to you soon again. Bye-bye, everyone.
Thank you.
Thanks a lot.
Bye-bye.
Bye.